Making basic data visualizations in Python is fast and straightforward. Making high-quality, professional-looking figures, on the other hand, has a habit of consuming hours of your life as you struggle to get libraries like Pandas and Matplotlib to do what you want them to do. By the end of this video, you'll learn an efficient core workflow to make best use of these libraries so you can go from data exploration to final figure export 5 times faster. Whenever you're ready, grab your cup of tea and let's dive straight into it. There's a very good chance you're using Pandas to organize and manipulate your data before plotting. In addition to being a great framework for managing tables of data, its plotting API makes it incredibly easy to spin up prototype visuals to explore your data and figure out the best way to tell its story. Let's start with some synthetic data points to represent measurements from an experiment with 2 conditions. We'll have 2 attributes and call them time and value for now for the sake of simplicity. Let's put these measurements in a data frame along with corresponding data labels. At the end, we'll use Matplotlib to draw a high-resolution figure canvas that will automatically be exported as a PNG file. For now, if we just want to create a basic plot to view our data, using the data frame's built-in plot method is incredibly convenient. We can see the points, but our x-axis represents time, and I want to draw lines connecting the points to show that they're in a connected time series. Immediately, we run into our first issue. As is, the data frame can't detect that our data points belong to 2 different data labels, and is treating them as if they're from a single series. They're plotted as the same color, and the line jumps from the last point of the first label to the first point of the second label. If we want to use color to communicate the difference between our data labels, we can brute force it by adding a new attribute to our data frame. This will dictate the color that each point will be plotted as. This works alright for the scatter plot, but we have a problem trying to extend the same logic to our normal plot method. It's not able to parse out that we want to use the color attribute to denote the color of each line segment, and it thinks we're trying to paint the line with a color named colors instead. Instead of diving down a rabbit hole to finesse the Pandas plotting API to do exactly what we want, we'll save a lot of time by using the Matplotlib library directly. This will give us much more precise control over how we draw the figure. We can still keep all of our data in a data frame, and in fact this is going to save us a lot of time later. I'm going to create a Matplotlib canvas using subplots, which will let us use the fig and ax handles separately to build the figure. Since we just need a single panel, I'll specify that we want 1 row and 1 column as positional arguments. Starting with a basic plot, we can quite easily get our scatter points and lines on a single canvas using the ax.dot syntax. However, our plotter is still completely agnostic to the fact that these are 2 separate populations of data points. One way to address this is to use Pandas' database-like functionality to contrive a relatively convoluted but effective way to filter the data frame to separate our 2 conditions and plot them that way. There's a much better way to group our data, which we'll go over soon, but for now, the query method works, so let's use it. I also want a legend for this data, but when I invoke the legend method, it's empty. Let's fix this by using the label keyword so that Matplotlib knows that each plot object should be named. That's better, but now we have both the scatter points and the lines appearing in our legend, and that doesn't look very clean or professional. One way to solve this would be to export the figure and redraw the legend in another program, like Illustrator or PowerPoint, but we can save a lot of time by correcting this in our script instead. We'll fix the legend in a moment, but first let's fix this mess that we're writing using query. In this example, our data is quite simple, and already this block of code is quite hard to read. As you can imagine, this technique is going to perform terribly when scaling to more complex datasets. Instead, let's use a different built-in data frame method, GroupBy. GroupBy works similar to the query that we were running, but it creates an iterable of distinct views of our data frame based on whichever attribute we're using as the argument. If you've worked in SQL and used the GroupBy syntax in queries, this method works in a very similar way, but for data frames. You may have seen GroupBy before, used to perform aggregate data operations like taking the mean of a column. GroupBy is very useful in a variety of Pandas data processing workflows, but the functionality we're most interested in here is linking the appearance of specific data attributes in our plots. Since we want to color our data by condition, we'll group by the condition attribute. From there, we can simply loop through the iterable generated by the GroupBy method, which will give us both the label of the group and the view of our data that's filtered by that attribute and label. I'm being verbose with the names of the label and the data frame view objects that we're getting from the grouped variable here, but we'll shorten these variable names later. As you can see, Matplotlib is assigning different colors to our different conditions automatically, and the same goes for when we plot the lines showing continuity between the data points of our 2 conditions. I personally am not a huge fan of the blue and orange, so let's bring back the custom black and red from before. For now, we'll put them in a list that we can iterate over and combine that with our iteration over the grouped variable using zip. Let's add back our label using the label keyword argument from before, and we can auto-populate this with the label variable that our grouped iterator is yielding. This is working, but we're reminded again that our data labels are using an internal shorthand notation that doesn't look very professional. Let's add another list containing our nice looking data labels and add these to our zip. Much better. I mentioned before that we probably don't want to be duplicating our data labels in our legend when it doesn't really provide any valuable information. We can disable one of our plotting methods from adding its labels to the legend by replacing its label argument with none. Now we only have the scatter points appearing in the legend, and it looks a lot nicer. To stay organized and make it dead simple to quickly make changes, I actually prefer to use dictionaries to map which colors, marker styles, and display names are used for each data label. Here I have a configuration dictionary mapping each data label to color and marker styles I want to use, which I'll pull out individually in the plot function. This way, all of the style settings are in the same place, making it fast and easy to modify as we refine the figure. Next, we'll want to add some styling to our figure title and axis labels. The standard way of doing this is to apply the configuration settings directly on each line. However, this is already a little tedious to tweak, and it's only a single panel. You can imagine that as our project scales to include multiple multi-panel figures, we'll want to keep the font settings consistent throughout. Going through final touches and needing to make font size changes can quickly turn into an hour-long process of making and reverting changes if we have dozens of hard-coded font settings scattered through a medium to large size project. Instead, let's replicate our previous solution of using a dictionary to manage all of our settings in one place. The magic sauce of this dictionary, though, is that we're going to be using keyword unpacking to cleanly inject our font settings wherever they're needed. To configure our font settings, I personally prefer to create a single nested dictionary. At the first level, we'll create a key value pair for each type of label, such as axis labels, tick labels, or plot titles. Within each, we'll create a key value pair using the keyword argument for each method's respective font formatter. For example, the keyword to specify axis label font size is font size, whereas the keyword for tick font size is label size. When we call each labeling method, we can grab the respective configuration settings and use Python's keyword unpacking syntax using 2 asterisks to automatically unpack our interior dictionary and apply the settings directly to the function call. Not only is this cleaner to read, but it also makes it a lot simpler to change all of our font settings in a single place and keep them consistent across all of our panels or figures. You could extend this technique to also use a dictionary to track all of your titles and axis labels, which would be useful if you find yourself repeating the same label name over and over in your project. But oftentimes, I'm using each label only once, so it's easier to keep the names declared in place for each plot. Once we're happy with how our plot looks, we're going to want to export it. When using the default settings for Matplotlib, our script will generate an interactive plot in its own window as we've seen so far. If we want to save this figure to embed in a poster, a presentation, or a paper, we can pretty easily just use the Save button on the window toolbar to write it to disk. However, regardless of how the figure canvas was specified in the code, saving the figure from the interactive window will actually only use the canvas size of the window the moment we hit save, not whatever we previously specified it as. This means that if the window is resized, it will save that resized canvas. What you may not have realized, and I certainly didn't until embarrassingly recently, is that the interactive plot renderer uses both canvas dimensions and the canvas DPI to determine how to draw that window. This is not noticeable if you always use the default DPI, but it becomes perplexingly apparent when you try to use a higher resolution like 300 DPI. This is because Matplotlib decides how big to draw the window in pixels by multiplying the canvas dimensions by the DPI. By default, it uses a DPI of 100, so with the default canvas size roughly 6 inches by 5 inches, at 100 DPI this renders at 640 by 480 pixels. The same figure at 300 DPI will render on your screen at 1920 by 1440 pixels. So if you're trying to draw a larger figure at 300 DPI, there's a very good chance that your screen does not have enough pixels to render the window and it will get automatically resized. This means that even if you don't manually resize the window, using the Save button will save the figure at a resolution or aspect ratio that you're not expecting. If you don't know that this is how the Matplotlib interactive window renderer works, it can be incredibly frustrating to try to sort out why the plot is not saving correctly. I personally have wasted hours trying to solve this problem before. The solution is to actually not use the interactive plot renderer at all. We're going to use a different Matplotlib backend altogether. The syntax for this is extremely simple. We simply tell Matplotlib to use the backend that we want instead of the default. There are a number of different options to choose from, which I won't go into here, but in order to save our figure directly to disk without rendering a window, we'll use the anti-grain geometry or AG backend. I like to create a boolean flag at the top of my plotting scripts to specify whether I'd like to work in preview mode, where I can see the figures in an interactive window as the default, or if I'd like to save the figures directly to disk with the AG backend. As an added benefit, if you need to create a dozen plots in one go, or you're simply tired of closing your plot windows, using this backend will prevent those pop-ups from appearing altogether. I like to do one last preview of my figure at a lower resolution so it renders properly on my screen, then restore the high resolution canvas setting and set save to true. And with that, a workflow for a clean, professional figure made quickly with Matplotlib. In this video, we used GroupBy to neatly aggregate our data from a Pandas data frame, then use those group labels to pull appearance settings from a dictionary to style our plot elements. We used the label keyword argument to override the default data labels, and assign label to none on the plot elements that we didn't want added to our legend. We used keyword argument unpacking from a font configuration dictionary to efficiently format text across a project, and change which Matplotlib backend we were using when it was time to export our figure. By adopting some or all of these techniques in your Python plotting workflows, you're going to consistently make high-quality, professional-looking figures in a fraction of the time. If you'd like to learn another technique to spend less time debugging and more time designing, check out this video. And if you'd like to continue writing clean, scalable Python code with me, please let me know with a like on this video, and maybe even consider subscribing. Peace.